Hello everyone, today we will learn about the climate system. In this lecture, we will talk about the components of a climate system and how each component influences the climate system. First, what is climate? Climate describes the average surface temperature and precipitation conditions and their variations during the cycles of solar forcing. Climate measures the daily and seasonal statistics of atmosphere temperature, humidity, cloud cover, rate of rainfall, wind speed, and other weather conditions. Here, I would like to emphasize the average and the statistic. The difference between climate and weather is that the weather only describes the condition of the day or of the hour. It has less significance to the long-term conditions. The climate has little significance to the day-to-day weather, but describes the statistical average weather conditions in the long term. For example, some argues against climate warming using a specific cold winter as evidence. This argument is a good example of confusing climate with the weather. A very cold winter is a relatively short term in the scale of weather, while climate describes the long term in the scales of tens or hundreds of years. Therefore, if we compare the statistic climate data of the pre-industrial time to that of the present, we can see increase in sea level, mean annual temperature, and the frequency of storms and the tornadoes, all of which showing the evidence of global warming. The climate system includes all parts of the Earth system, including the lithosphere, hydrosphere, cryosphere, biosphere, atmosphere, and the solar heating, and their interactions in the space and time. To be specific, the lithosphere interacts with the atmosphere, that mountains affect wind and precipitation patterns, and the land-to-sea distribution influences atmosphere circulation. The oceans, which is the majority of the hydrosphere, store and transfer heat globally. The atmosphere controls the heat and the moisture transportation by wind and also influences the global temperature through greenhouse gases. Other factors such as solar heating and surface orbital also play important roles in climate system. We will talk about them one by one. First, let's talk about the atmosphere. The atmosphere composes 78% of nitrogen and 21% of oxygen. The rest 1% composes argon, carbon dioxide, water vapor, ozone, methane, and etc. So the greenhouse gases is only a small portion of the atmosphere. Among them, the most abundant greenhouse gas is water vapor. The most effective greenhouse gas is methane, but it is also the least abundant. Carbon dioxide is the most attention-drawing greenhouse gas of today is because human activities burning fossil fuels has significantly increased its concentration in the atmosphere, and considerable magnitude of temperature increase can be detected due to human activities. The atmosphere transports the heat and moisture from the tropics to the pole. The atmosphere circulation and the precipitation patterns dominate the pattern of climate zones on Earth, although they are only less than 1% of the atmosphere. The greenhouse gases, especially the carbon dioxide, have a significant effect on global temperature. Here in this picture shows that the global temperature anomalies strongly correlate the increasing of carbon dioxide concentration in the atmosphere. The greenhouse gases play an important role in keeping the Earth warm and livable. Without greenhouse gases, the Earth would be at least 33 degrees colder than it is today. In the following video, you will see how greenhouse gases work to keep the Earth's surface warm.
The Earth and the Moon are basically the same distance from the Sun, yet temperatures on the Moon average an unlivable -18 degrees Celsius. And even deadlier, they range from -170 Celsius during lunar night to 100 Celsius at lunar noon, regularly exceeding both the coldest and hottest temperatures ever recorded on Earth. And while the days and nights on the Moon are about 14 times longer than those on Earth, our planet's relatively fast rotation isn't what spares us from those loony temperatures. What protects us is our atmosphere. By day, it serves as a shield, blocking out the most harmful and energetic of the sun's rays and about 1/3 of the less intense but visible light. At the same time, it traps the infrared radiation, aka heat, radiating out from Earth's sun-warmed surface, keeping us from freezing solid at night. In order for our atmosphere to absorb any kind of radiation, it needs to have some electrically charged particles for passing electromagnetic waves to push around. And most of our atmosphere is made up of gas molecules that don't have an electric charge. They all have a balanced number of positive protons and negative electrons. But some molecules hold most of their negatively charged electrons closer to one side, lending them a lopsidedness that can jiggle back and forth to absorb the energy of incoming infrared rays. For example, water, ozone, and nitrous oxide are all electrically lopsided, so they all absorb infrared radiation. Then there are gases like carbon dioxide and methane. On paper, neither molecule looks lopsided, so it doesn't seem like they should be able to absorb any radiating heat. But in reality, gas molecules aren't motionless. They crash into each other billions of times per second, knocking each other in different directions and also into different modes of rotation and vibration. And it turns out that both carbon dioxide and methane spend most of their time shaking it in electrically lopsided ways, allowing them to absorb infrared rays and help insulate the Earth. Even though many different kinds of molecules can absorb infrared radiation, the vast majority of our atmosphere can't, because it's made of nitrogen and oxygen, which don't get lopsided even when they are vibrating. They're too symmetric. Nevertheless, the lopsided 1% are such good infrared absorbers that they manage to intercept about 90% of Earth's outgoing heat. Each captured ray gets pinged around the atmosphere, and most end up returning to the surface at least once before escaping to space. We don't need to visit the moon during frigid lunar night to know just how important the game of radiation pinball is for Earth. Ice records from our own coldest climate show that small natural variations in atmospheric carbon dioxide produce relatively big changes in temperature. They also show that, compared to the last 800,000 years, the game today is much, much harder.
From this video, we can see that increasing the concentration of the greenhouse gases in the atmosphere could increase the greenhouse effect. With the increasing in temperature due to enhanced greenhouse effect, the water vapor content in the atmosphere will increase because warmer air has a higher capacity of water vapor than the cold air does. The water vapor is also a type of greenhouse gases. Therefore, increase of greenhouse gases in the atmosphere will lead to temperature increase, which will lead to further increase of greenhouse gases and subsequently of the temperature. So, the effect of greenhouse gases has a positive feedback loop, which means the result of increasing greenhouse gases fall in the loop of further strengthening the greenhouse effect. One effect of rising carbon dioxide concentration in the atmosphere is the possibility to break the balance of ecosystem in the ocean. As the biggest sink of atmosphere carbon dioxide, the ocean dissolves carbon dioxide and form bicarbonate and hydrogen ions in the ocean. The excessive hydrogen ion leads to dissolve of carbonate minerals in the ocean, which includes coral reefs and carbonate platforms. Coral reefs and the carbonate platforms are important living habits for shallow marine organisms. Destroying the shallow marine habitats could damage the ecosystem of the marine environment. Hydrosphere. The hydrosphere includes the ocean and the fresh water. The ocean takes 97.5% of the entire hydrosphere. The rest 2.5 is fresh water. Among the fresh water, the ice caps and the glacier takes 1.8% and the groundwater takes 0.63%. Lakes, rivers, and the water vapor in the atmosphere only takes less than 0.07% of the hydrosphere. Let's see the ocean first. Ocean current serves an important role in transporting heat in the global scale. Ocean is also the dominant source of freshwater precipitation on land. Heat and precipitation are everything about climate. The ocean current include the surface current and the deep current. The surface currents are primarily driven by wind, and it only influences the top 400 meters depth of the seawater. The global wind pattern and atmosphere circulation influences the ocean currents. Heat is transported by the ocean currents, and the heat could modify the air temperature, which is the driver of the winds. So, ocean current can influence wind. The surface current and the global wind patterns are influencing each other, and the interactions between them influences the climate. A typical example that resulted from the interactions between the ocean current and the wind pattern is the El Niño and the La Nina oscillation cycle. Here's a video that explains the El Niño effects.
Every few years, the El Niño phenomenon kicks into life in the Pacific Ocean around the equator. It can affect weather around the world, changing the odds of floods, drought, heat waves, and cold seasons for different regions, even raising global temperatures. But what is El Niño and how does it happen? Firstly, we need to know what's normally happening in the tropical Pacific. This vast stretch of ocean sees consistent winds called trade winds that blow from east to west. These winds push warm water near the surface in their direction of travel, so the warm water piles up on the western side of the ocean around Asia and Australasia. On the other side of the ocean, around South and Central America, as the warmer water gets pushed away from the coast, it's replaced by cold water which is pulled up from deeper down in the ocean, a process called upwelling. This creates a temperature difference across the tropical Pacific, with warmer water piled up in the west and cooler water in the east. Warmer water adds extra heat to the air, which causes the air to rise with more vigour, and it's this rising air that creates an area of more unsettled weather, with more cloud and rainfall. That rising air in the west sets up atmospheric circulation across this part of the world, with warm, moist air rising on one side of the ocean and cooler, drier air descending on the other. This circulation reinforces the easterly winds, so this part of the world sits in a self-perpetuating state until El Niño begins. If conditions are right, tropical Pacific weather systems, or slow changes in the ocean around the equator, can set off a chain of events which weaken or even reverse the usual trade winds. With weakened trade winds, there's less push of warm surface water to the western side of the ocean and less upwelling of cold water on the eastern side. This allows the usually colder parts of the ocean to warm, cancelling out the normal temperature difference. Because the area of warmest water moves, so does the associated wet and unsettled weather. This changes rainfall patterns over the equatorial Pacific, as well as the large-scale wind patterns. It's this change in winds which has a knock-on effect, changing temperature and rainfall in locations around the world. The main impacts are around the tropics, where you see an increase in the risk of floods in Peru and droughts in Indonesia, India, and parts of Brazil. But virtually wherever you are in the world, El Niño has the potential to affect you directly via the weather or indirectly via socio-economic impacts. There's another impact from El Niño which happens because of all the extra heat at the surface of the tropical Pacific. This releases vast amounts of energy into the atmosphere, which can temporarily push up global temperatures. This is why El Niño years often feature among the warmest on record. Each El Niño event is different, so the global impacts can change. You can find out more about the differing impacts of El Niño on our website. El Niño peaks around Christmas time and lasts for several months. It can die back to neutral conditions, but sometimes reverses into La Niña. This is the flip side of the oscillation, which sees a strengthening of the normal trade winds. This pushes the warmest water to the far western part of the tropical Pacific and increases the upwelling of cold water in the east. This cooler water extends out from the coast of the Americas towards the central part of the ocean. La Niña also impacts global weather and tends to have opposite effects to El Niño. You can also see more about La Niña and its impacts on our website.
During the strong El Niño years, here in Texas, we are expecting to see cool and wet weathers more frequently. And during the strong La Nina years, we expect to see warm and dry weathers more frequently. The deep sea currents are also called thermohaline circulation. So the deep sea currents are controlled by the thermal and the salinity gradients of the seawater. Both of the temperature and the salinity ultimately will influence the density of the seawater, and the density contrast is the primary driver of the deep ocean current. The turnover rate of the deep ocean currents are much longer than that of the surface water current. It takes hundreds to thousands of years to circulate deep oceanic water. This long turnover cycle also delays some aspects of feedbacks to the climate change. For example, ocean is the largest sink of carbon dioxide. The capacity of dissolved carbon dioxide in the ocean is controlled by the seawater temperature. The low temperature deep sea is where the carbon dioxide goes. However, once the deep sea water temperature increases after circulation in the next several hundred years, the carbon dioxide might be released from the deep ocean back to the atmosphere, which will speed up the global warming. Cryosphere is the largest freshwater reservoir in the hydrosphere. It includes ice caps, glaciers, floating ice, sea ice, and frozen lakes and rivers. Ice caps and glaciers takes up to 72% of fresh water on Earth's surface. It is also the reason that sea level is in danger of rising to flood coastal cities during global warming. Lithosphere. Lithosphere interacts with the atmosphere in several ways to influence the climate. Number one, lithosphere has a lower heat capacity compared to the ocean. Therefore, the lithosphere re-emits more heat to the atmosphere after absorbing solar radiation. Number two, topography influences atmosphere circulations. The rain shadow effect suggests that more precipitation on the south side of the mountain range than that on the lee side. So the precipitation patterns are influenced are influenced by mountain orientations. Number 3. Volcanic eruptions eject dust to the atmosphere. The reflectivity of the dust is very strong, and the solar radiation will be reflected more if more dust is suspended in the air. So the eruption will lead to climate cooling due to the increased dust level in the atmosphere. Number 4. Weathering rocks consumes dissolved carbon dioxide, which is the bicarbonate, and subsequently drives more the carbon dioxide in the atmosphere dissolved into water. Therefore, weathering consumes greenhouse gases and driving the climate to cooler conditions. Biosphere comprises all organisms living near the Earth's surface, plants, animals, and microbials, both marine and terrestrial. The biosphere is coupled to a climate system through its interactions with the atmosphere, hydrosphere, and lithosphere. Life also regulates the composition of the atmosphere, including greenhouse gases such as carbon dioxide and methane. Through photosynthesis, marine and terrestrial plants extract carbon dioxide from the atmosphere. Some of it is precipitated as shale made of calcium carbonate or buried as organic matter in the sediments. The biosphere thus plays a central role in the carbon cycle. In the carbon cycle, the lithosphere releases carbon to the atmosphere and the hydrosphere by volcanic eruption of carbon dioxide and weathering rocks and dissolving bicarbonate in water. Photosynthesis fixes carbon dioxide to organic matter, and aquatic organisms fix dissolved carbon dioxide, the bicarbonate or carbonic ions, to carbonate minerals and limestones, ultimately consumes carbon dioxide from the atmosphere. However, human activities disturb the carbon cycle. Burning fossil fuels emits excessive carbon dioxide to the atmosphere. Land use in agriculture and industry reduces the uptake of carbon dioxide from terrestrial plants. In addition, as the carbon dioxide concentration in the atmosphere increases, the ocean is acidified and in danger of dissolving existing carbonate minerals and limestones in the marine environment, which will lead to emitting more carbon dioxide to the atmosphere. So carbon dioxide to the climate has a positive feedback loop, and the greenhouse effect will be strengthened and amplified in the feedback loop. Solar radiation is the driver of a climate system. The Earth receives about 340 watts per meter square heat energy per year, and to maintain a relative constant temperature, the Earth's absorbed and re-emit heat are equivalent. In the picture, you can see that about half of the solar radiation is absorbed by ground and the atmosphere, and half is reflected by the clouds and the surface of the Earth. Meanwhile, the Earth is radiating heat back to the atmosphere, a majority of which is reflected back and kept in the atmosphere because of the greenhouse effect. Therefore, the greenhouse effect is the key to balance the heat and keep the Earth to a constant temperature level. Although we know that the solar radiation is not constant through time, the rate of changing in the intensity of solar radiation is in billion years scale, and we can assume that the solar radiation does not change in a million years scale. If that is the case, we found that the solar radiation to the Earth is still not constant. The solar radiation to the Earth is also controlled by the orbital positions of the Earth and its self-rotation angle of the Earth towards the Sun. The effect of the combination of the two factors also influence the solar radiation intensity to the Earth. The orbital positions and the rotation angles have their own cycles. The resulted cyclicity effect on climate is called Milankovitch cycles. In the following video, it explains how Milankovitch cycles influence the climate.
Over Earth's long history, there have been dramatic changes to our climate. The ice ages have come and gone. And what's surprising is that there's a strong pattern that explains why ice ages happen when they do. This is called the Milankovitch cycle. Named after Milutin Milankovitch, his theory explains how the Earth's climate changes over hundreds of thousands of years. His theory is based on two key ideas. First, the Earth's climate is strongly affected by how much sunlight the northern latitudes receive during the summer. Second, this amount of sunlight varies based on changes in the Earth's orbit and rotation. Why are the northern latitudes so important? It's because of ice. When sunlight hits the ground, most of the energy is absorbed as heat. But if the ground is covered in ice, most of the light reflects away because ice is white. This creates a positive feedback loop. Ice forms when it's cold, but ice also reflects light, making it colder, which forms more ice. So ice is really important for climate. The northern and southern hemispheres both contain lots of ice, but there's more ice in the north because there's more land. Land has a lower heat capacity than water, which means that water doesn't change temperature as easily as land does. This is why coastal regions are generally more mild and why ice forms more easily on land. Just look at the difference between the northern and southern hemispheres. In the south, there are ice caps that grow during its winter, but not nearly as much as they do in the north. During the winter, the land above the Arctic Circle is covered in darkness, experiencing twilight 24 hours a day. It's very cold, and lots of ice forms during the winter. And this is true no matter what's going on with Earth's orbit. The key variable here is how much ice melts during the summer. This depends on how much sunlight there is during the summer. Now, you might think that this doesn't change, but it does. Milankovitch showed that over hundreds of thousands of years, the amount of summer sunlight can shift plus or minus 15%. This can bring ice ages. This can end ice ages. How can the amount of summer sunlight be changing? Well, first, the distance from the Earth to the Sun is changing. And second, the Earth's tilt is changing. The Earth's axis is currently tilted at 23.5 degrees, but this changes. Other objects influence the Earth gravitationally, nudging its tilt up and down. Every 41,000 years, it cycles up and down. When the Earth is more tilted, there's more sunlight during the summer. More summer sunlight means that more of our ice melts away. With less ice on the ground, less light is reflected away, giving us a warmer climate. Earth is unusual in that its tilt doesn't change very much. Earth has a very large moon, which stabilizes its tilt. Mars has 2 tiny moons, and so its tilt changes much more dramatically. The next effect is the distance from the Earth to the Sun. The Earth's orbit is not a circle, it's an ellipse. Every 4th of July, we celebrate aphelion, the day that the Earth is farthest from the Sun. Then in January, the Earth moves closest to the Sun. Now the planets Jupiter and Saturn both nudge the Earth, causing its orbit to shift slightly, becoming either more oval or more circular. This happens over a period of 100,000 years. This effect is wildly exaggerated in this diagram. It actually looks more like this. You can barely even see that the distance to the sun is changing, but this subtle change has important consequences for our climate. Earth as a whole receives 6% more sunlight during January than it does in July. The seasons change because the North Pole sometimes tilts towards the sun and sometimes tilts away. The change in the distance to the sun, this works against the change in the seasons. This moderates the seasons in the north, since the Earth is furthest away in July. But this was not always true. The Earth's axis is moving in a circle. It's spinning like a top. This is called precession. In fact, I made an entire video about this. And what this means is that 13,000 years ago, the tilt of the Earth was reversed. When the Earth was closest to the sun, it was summer in the north. The distance change didn't oppose the seasons, it amplified seasons, making them more extreme. Now, warmer summer means more melting. More melting means less reflection, which means the climate as a whole is warmer. The amount of summer sunlight is affected by 3 long-term cycles. 1 changes the tilt. 1 makes our orbit more circular or more oval. And 1 changes how the distance to the sun matches with the changing of the seasons. These 3 cycles powerfully impact our climate. Scientists have measured the history of our climate using ice cores. Now, Earth's climate is complicated. You can't just reduce it to a single input. But the Milankovitch cycles have played a key role in our climate for hundreds of thousands of years.
From the video, we know that there are 3 cycles in Milankovitch cycles. The eccentricity, which is the cycle of changing the shape of the Earth's orbit, is 100,000 years. The precession, which is the cycle of wobbling of the Earth, is 23,000 years. The tilt, which is the cycle of the self-rotation angle to the orbit plane, is 41,000 years. The effect of combining these 3 cycles results in the force from solar radiation driving the climate to greenhouse and icehouse ages. The last glaciation in Pleistocene Ice Age is primarily driven by the Milankovitch cycles. The intervening glaciation and the interglaciation periods follows the oscillations of Milankovitch cycles. Orbital. The orbital describes the percentage of heat that is reflected back from the Earth's surface. For example, ice has a very high orbital because it absorbs very little heat and has a very reflective surface. Water, on the other hand, has a very low orbital because its heat capacity is very high. It can absorb most of the heat energy and reflect back very little portion. A rise in temperature reduces the accumulation of ice and snow in the cryosphere, which decreases Earth's orbital and increases the energy its surface absorbs. The increased warming of the atmosphere enhances the temperature rise. This is another example of a positive feedback loop. Okay, in this lecture, we have discussed the components of a climate system and how each component influences the climate. I hope you enjoy this lecture and see you next time.